we begin today's class. So, and of course, if at any time you have any issues, feel free to stop me, and hopefully I'll be able to clarify whatever the matters are. So today we're going to start talking about oscillators. Now, oscillators, is a type of waveform generator. We spent some time last week looking at other types, which were the square wave, the multi-vibrator circuits, the triangle wave circuits that we looked at some time before. So this one, the oscillator specifically, is more or less generally accepted that when you talk about an oscillator, you're generally talking about something that is going to give you a sinusoidal output waveform, right? And particularly, what we want here is that these oscillators, once you turn it on, it starts generating the output for you. Remember last week when we spoke about the multivibrators, for argument's sake, you had to trigger to get a pulse, or you had to make some sort of change on the input in order to get the output. And then there was some that were free running where we took output and sent it back and so on. A similar thing will happen here. Oscillators are all over the place, all right? The fact that we are able to communicate with the laptop over a network, or you have your cell phone, or however you're listening here, all of that is a tribute to oscillators in communication systems and in the computer systems itself, right? So in communications, for instance, the transmitter frequency, actually is printed a little bit wrong in the third line here, but the transmitter frequency that you use up in the gigahertz range. Now those are actually sinusoidal high frequency signals and so on. And it is because of that that we're able to send signals from one point to another. And then in the computer itself, there are oscillators that are running, some sinusoidal, some not. And they also are functioning to keep the system going along as it is. Oscillators, typically you get frequencies that range from sub-hertz, which are fractions of a hertz, very slow varying signals, to extremely high, in the high gigahertz range. And in many of the applications, you require low distortion. Distortion means that the sinusoid itself is, if you have an oscillator and it's producing a particular frequency sinusoid, that is the only frequency that it is producing and nothing else. Now, when we do Fourier series and the Fourier transform in ECNG2012, you're going to see where those wide distorted signals start to give you other frequencies that you didn't want in the first place. So we will spend some time looking at that and hopefully be able to tie it back to things that we did here as well. Right? There are two main classes of oscillators. There are those that use a resistor capacitor network of some form to set the oscillation frequency. And there are those that use an inductor capacitor arrangement to generate the frequencies as well. Usually the RC oscillator operate from very low frequencies up to moderately high megahertz. So they're useful in audio applications and in some low frequency communication applications as well. The LC operation oscillators, are the ones that they tend to use in communication applications. So in radio applications, in two-way communications and the like, right? And they're very specialized. We may touch on it, but not in too great a depth. I think what happens is that once you understand the principle of operation of the oscillators here, some of those things you can actually pick up and read and figure out how it works very, very quickly if and when it comes up. Talking to the people in the communication courses, both here at level 2 and in level 3, just to make sure that they are, if there's any other things that they want us to cover here, just to make sure it's included as well. All right. So you've seen this before and you're going to see it again. right? So this may be the second or third time, and you're going to see it again. This identical diagram in ECNG 2011, those of you who are doing it with me also. It comes up with reason. This is a block diagram of a system in the S domain, and we mentioned this when we were talking about feedback. We use this to model transfer functions, and we spoke about transfer functions themselves this morning a little bit. All right, so this particular block diagram, you have two sort of blocks in it. One is a forward block, and somehow the transfer function for that block is G, and the block that is feeding back, and we learned that term and we use that many times already. There's a block that is taking some part of the output Y, and that block also has its own transfer function H, and out of H is feeding back a signal Y1 towards this unit here. And this unit here, we said already, is something that we call a summing junction. And electronically, you know that that's possible. That's an op-amp. It's an op-amp circuit where you have multiple inputs coming in, for instance, on the inverting input, and you can and the op-amp sums whatever comes in. So you can sum and invert, or you can invert first and then sum, however you want it. So this particular one is an example, as we said, of negative feedback, because whatever is taken from the output is processed a little bit, but this here, it is subtracted from the input. So we have an input here, and we are subtracting some part of the output from it, right? And when that is the case, we said that the negative feedback systems have a tendency to regulate or control things. So if I made a change in X and Y, and we use this for the power supply discussion, and Y is going off, varying in some form or fashion, part of Y is coming back. And if Y is doing exactly what we want, then this little signal here, X1 of S, will be 0. Oops. Will be 0. It means everything is all right. If Y varies off of whatever we wanted, then X1 is going to have a value somehow, and it's going to go through G and cause Y to change. And this is the principle that we used in the regulated power supply, either the one with the op-amp or the one with the transistor feedback. Right? So, and it's easy to show, and we will do it again in signals. It's very easy to show that Ys is Gs over 1 plus Gh by Xs, right? So the negative feedback gives me a positive sign below here. And as I said, it's very easy. The proof really is to get everything in terms of Y1 and X1, and then eliminate Y1 and X1 from the equation, and you'll end up with that. So G, sometimes we say G instead of GS, or G of S is easier to say, so G over 1 plus GH. Right, so here's another version of it. So here's one now where it's a closed loop system again, closed because we have a complete, there's nothing flowing back, there's an input and output, and the feedback comes back and goes back into the system. The diagram is showing this one, and there's an amplifier now, so the amplifier has a transfer function AS, and the feedback is a feedback network or another piece of electronics, and it has a transfer function beta S. And this one now, we have a positive sign. So this is a positive feedback system. And as we kind of summarized, the overall, when you simplify the block diagram, the positive feedback system now gives you A over 1 minus A beta. So negative gives you a positive sign below, the positive gives you a negative sign below. Now, the thing about positive feedback, and we mentioned those already, is that, okay, so it's taking part of the output and sending it, it's taking the output, is sending it through this network here, and the network is doing something and sending back a signal here. Now, whatever it sends back is going to be added. to X. So it sends back and it adds. So it is Xi plus something. That goes into here if there's an amplifier again. So X gets bigger. A little bit comes back in here. So it keeps going and getting bigger and bigger. And this is where the positive feedback of the circuit comes in, or of the system, sorry, the model comes in. All right. At some point in time, of course, this is going to keep until it can't increase anymore. The upper limit on most of these things is whatever, if it's electronics, is whatever the power supply happens to be, right? If it is something electromechanical or something powered from the power line and so on, it's going to go and reach some sort of maximum and either blow the fuse or just stay at the maximum because it simply can't go any further because whatever is supplying it just can't supply more and more power to it. Now, if this now is usable on just an alternative model, sometimes in electronics textbooks, they draw the model like this, so they amplify it. It's an accepted sort of symbol that an amplifier is a triangle, is like the outline of an op amp, right? So an amplifier, anything looking like that, typically you assume that it is an amplifier of some sort. So they use a forward block as an amplifier, the triangle, and the feedback block is still the normal square coming. And they call AB or AS beta S the loop gain. Right, so anytime you see a block diagram somewhere, once you get it down to this, and we're going to spend a lot of time in the other course simplifying block diagrams to get them into this final form here. Once you get it into that final form here, 1 minus or plus, right, AS beta S, or when we started off G and H, the AS beta S or the GH from the first couple of slides is what we call the loop gain of the particular system. Now, how all of this helps us now is that if we make the loop gain 1, think about it. If the loop gain is 1, right, look at the transfer function here. If AS beta S is 1, then the denominator now goes to infinity. So AS over infinity means that the output is incredibly large at that point in time. So just before that, what is basically happening here, of course, this is all theoretical. If we get the loop gain AS beta S to be equal to 1 somehow, then what we have is a system that we can get an output essentially with little or no input. Right? We know, of course, that is you're going to have to do something because you can't get something for nothing. But you're going to be fairly close to that sort of ideal, that you have little or no input and you have an output that is working or running away from you in some form or fashion. Yeah? That is what they call, fancy term, the Barkhausen criterion. So a system looking like that with a simple block diagram, notice how we remove the input from it, just for illustration purposes. If you have a system where you have the loop gain AS beta S, or in the more general term, if this is GS and this is HS, right? If GH, I've left out the S, is equal to 1, or as we have in the diagram here, A beta S is equal to 1, right? This is something called the Barkhausen criterion. And basically, what we need, we're going to use that to make this thing oscillate. Once we get GH equal to 1, we know that in theory, we're getting the system being almost self-sustaining now. More formally, because A and beta or G and H are complex variables, usually the magnitude of GH or A beta S is 1. So the absolute value, the magnitude is 1. And then the phase, in order for us to have positive feedback, whatever leaves the output and comes back into the input has to be in phase with whatever is going on. Remember, in phase signals add, right? So if you have two signals and they're exactly in phase, then when you pass them through the circuit, one is going to add to the other one and the amplitudes increase. If they are totally out of phase, then they cancel. All right, and if they're not exactly in phase, then you get some other funny behaviors happening inside of there, and the system will generate, and you know it already from your physics, something called beats, right? That was the process of generating beats. So for the signal, first off, whatever comes through the feedback loop, the phase going through that whole loop there has to be a multiple of 2 pi. In other words, if there's no phase shift, in other words, what goes out comes back in identically to when there's fine, no phase shift, 0 degrees. It is the kind of thing you will get with a purely resistive network. But if you have other components in there somewhere, then you have to have a way of figuring between A and beta to make sure that the entire phase shift as you go around the network is a multiple of 2 pi, so that whatever you are feeding back is totally in phase with whatever is being generated inside of the system, so that it continues reinforcing itself. So if we have these two things, if we have somehow we're able to achieve these two things in our design, then what we're going to have is a circuit that produces an output self-sustaining without us producing an input. And what we're going to do is now to see how to make that output sinusoidal. Everybody following? Yeah? And because, of course, that AS and beta S are frequency-dependent components, only at some particular frequency would the criteria that the magnitude of AS and beta S be equal to 1, and that the phase of the whole AS beta S feedback, the loop gain, would also be a multiple of 2 pi. So at that point, we're also getting our self-sustaining output, but happening at a particular frequency. So what should happen here, therefore, is that if the magnitude of A beta, and a little bit of shorthand here, the magnitude of A beta is 1 and Xi is removed, the system should oscillate indefinitely. Okay? If A beta is less than 1 and we remove the input, the output should die out. And if A beta is greater than 1 and we remove the input, the output will go to the whatever is the power supply rail voltages, and it will stay there, right? Or the system will shut itself down. At that point in time, it also becomes nonlinear. When it saturates, then the output is no longer a linear function of the input. And it's now you have difficulty in predicting what is going to happen. As usual in engineering, nothing is easy. So it's in this kind of thing. So making A be equal to 1 is difficult, right? Exactly equal to 1. We know components have tolerance values. We know that things vary with temperature, with voltage, and the like. So usually what we do is we compensate by going a little bit above. So we try to make A beta slightly greater, the magnitude of A beta slightly greater than 1. And then we do some other little magic with the electronics to prevent the saturation and nonlinearity happening. And we'll talk about that a little bit later on when in this whole discussion on oscillators. All right. So the conditions for oscillation: 1, you have to have positive feedback. So 1, you have to have positive feedback, right? 2, you have to have the loop gain the magnitude of the loop gain has to be 1. And then the third thing that you have to have is the phase of A beta must be some multiple of 2 pi. Yeah? Those are the Barkhausen, that is the Barkhausen criteria. And if you're able to get all three things there, 1, you have the system with positive feedback. 2, you make the loop gain, the magnitude of the loop gain equal to 1. And then the phase of the loop gain coming back has to be a multiple of 2 pi, so that you have, basically, you ensure this bit here. If it's not, then even if you add, then you're going to, if you add a negative number, if it's out of phase, then of course you cancel. And if it's slightly out of phase, then you get beats being created, and you do not get the positive feedback being created. Make sense? Any? Yeah? Right. So let's see now how we actually make this work in practice. So as I mentioned before, one of the most common types of frequency dependent, or one of the most common ways of making oscillators are to use RC resistor capacitor networks. And just to remind, we just did this, so these are just the same Barkhausen criteria here, the positive feedback, and this is what we said here. We know that if they are capacitors, they are reactive components, and then just a comment here, and we'll explore that a little bit later on as you get into the Fourier series. You may be doing that already in math, I'm not too sure. But as you go through the Fourier series, and we also do it here, you're going to see why it is that a system with reactive elements, why when you do certain things, then the only sort of waveform that will be preserved happens to be a sinusoid. So in other words, this kind of behavior with the Barkhausen criteria, you can't get a square wave, you can't get a triangular wave being produced. You must get a sinusoid. Okay? The phase shift usually is a frequency dependent function, so it's only at a particular frequency that we're going to get the 2 pi phase shift occurring, and that is where we get the sinusoid behavior coming up. So just in bold here, the summary of everything here. So the general principle for oscillators is that the frequency of oscillation is that frequency at which the total phase shift around the system is 0 or multiples of 2 pi, and the loop gain is greater than 1, is equal to 1, sorry, or maybe a little bit greater, right? Usually we have to do that, and this, of course, is, you know the word Barkhausen. Barkhausen criteria. If my memory from 150,000 years ago, I think there's something called Barkhausen radiation that you meet somewhere in physics, if I'm not mistaken. I don't know if you all ever came across it. Somewhere along the place? Nope. Okay, well, there you go. Too long ago. Right. So the first type of system or RC network that produces, yes, if I'm sure it does. It's somewhere in the right. There's something to do with radiation, and even those good old-fashioned fluorescent tubes produce Barkhausen radiation somewhere inside of there. But anyway, so back to business. One of the more common networks that we use to produce a sine wave, maybe. Okay, I'll put that as an extra point in the exam, right? Is a circuit called the Wien-bridge, right? Max. Well, actually, if it's German, you would pronounce it Wein, but it's actually Max Wein. The Wien-bridge oscillator, and it's based on a particular network called the Wien-bridge. Now, the Wien-bridge is actually, if you take out if you take out the op amp for the time being, and you look at this, these 2 points are actually connected. So we have a bridge with this and this on one side of the bridge, ignore the op amp, and this on the other side. So it's like a Wheatstone bridge where you replace 2 of the resistors on the arms with a resistor series, a series resistor capacitor combination and a parallel resistor capacitor combination. And right across the bridge point, if you remember in the Wheatstone bridge here, right? So we go on one point. In this case, normally in the bridge, we would excite here and you measure across here, right? So we're putting an op amp here. And because, as we said, there are certain conditions that we have met, the system doesn't need an input. So we don't need this. And somewhere along the road, we're supposed to be getting, we'll see how we get some oscillations being produced here. All right, let me just clear that a little bit. So it's based on the Wien-bridge network. Forget the op amp and the 2 resistors for the time being, and let's look at that little network shaded. All right, so the Wien-bridge basically is 2 parts to it. There's a series RC part, and then there's a parallel RC part. Notice that the input, there's an input there. The input is going into the series side, and the output is coming at the junction between Z1, which is a series impedance, and Z2, which is a parallel impedance. All right, and fairly simple circuit theory. You get that V out and V in are, of course, normal potential dividers, except that you're dealing with impedances here. Z1 is, of course, 1 R plus 1 over SC, and Z2 is R in parallel with 1 over SC. And if you substitute and you simplify and play around with it a little bit, you should get the equation up top that V out over V in is SRC over S squared R squared C plus 3SRC on plus 1. And we're going to see there's a little reason why we change it around so that the coefficient of S squared is 1. We'll talk about that in signals, but the preferred arrangement usually is to have the coefficient of S squared as 1. So to get that, we divide through by RC, and you get, oh sorry, by R squared C squared, and you get this version of the expression here. You could remember anyone, it's easy to derive as well. All right, so you could sort of remember that one, and you could work with that. There's no harm in it. It's just that for the analysis purposes is actually to have the coefficient of S squared. It's easier and more straightforward with the coefficient of S squared as 1. Right? Now, this type of transfer function has what is known as a band pass response. In other words, if I were to draw a graph of amplitude against frequency, right? So this is the amplitude of the response, and this is frequency here. As the frequency goes up, a band pass response does this. It doesn't pass anything. Then it starts to pass a set of frequencies, and then it stops again. In other words, there's a band or a zone that it lets frequencies through, and then outside of that zone, it doesn't. Right? We will meet some of that more formally when we do some active filter work later on in the course as well. Now, there's a standard form for it. Right? Like today, we started to talk about second order systems, and we were looking to see, remember this morning, those of you who were there, we saw that certain second order systems now, depending on the behavior of the second order system, that it could, you start in the S domain, that you had a e to the minus j omega t being created when you converted it back to time so that the system would oscillate. This is exactly what that's based on. Right, so there's the explanation, a more formal explanation for what's happening inside of here. So here's the standard equation for the bandpass behavior, right? It's something, a function in terms of omega 0. So we figure omega is normally the standard thing for a frequency. So omega 0, and then we have two other things here, G and Q. And almost standard nomenclature. G means again, and Q is something, just assume for the time being, Q is equal to 1. It is something called a quality factor. I don't know if you met that at all in circuits before. Anybody? You met that when you were talking about inductive circuits or anything like that? Did you come across something called quality factor? Yeah, I know. Can't remember. Right. So this is the quality factor. The quality factor has to do with especially in inductive circuits and so on, and has to do with a certain behavior of the impedance of the circuit. But anyway, we could assume that Q is equal to 1 for the time being here. So if we compare both equations here, then we can see that the equation on the left is the one that we derive for the Wien-bridge. The equation on the right is a standard form of that equation. If Q is 1, then what we can see in comparing the two circuits is that omega 0 is 1 over RC. And we call that the center frequency for this particular arrangement, this little circuit arrangement here. And then G, as you know, G is a gain. And if you put omega 0 into the equation there, then you find that V out over Vn at omega 0, in other words, make omega 0 1 over RC, you get that the gain now, V out over Vn, is 1/3. So in other words, this circuit has a gain of 1/3, and somewhere along in this response that it has, there's a center frequency that is given by 1 over RC. Fair enough? The derivation is easy. The only thing that we didn't derive and we're using is this, right? And just making a comparison between one and the other. So let's see how that, we're going back now to the Barkhausen criteria business. So if you remember when you did the Laplace transform, that Laplace variable really is a two-part, the Laplace variable S is really a two-part variable. It has a real part sigma and an imaginary frequency dependent part, which is j omega. So to get the frequency response of that transfer function up here, we're going to make the substitution S equal to j omega. And we will get, that is really doing something called the Fourier transform for it. And we're going to have the full complete explanation for that in ECNG2011. But I'm using the answer here. So for the time being, accept that when you have a transfer function that is a function of S, if you want to find out how that transfer function varies with frequency, you substitute X with j omega. Omega, of course, you know omega is 2 pi f, so that is your frequency variable there. The omega here is in radians, or I could get it in hertz by using the 2 pi f substitution. So if you substitute S equal to j omega inside of there, and you manipulate it a little bit, you're going to get the transfer function now in terms of frequency being j omega over minus omega squared plus 3 j omega over RC plus 1 over R squared C squared. And if you plot this now, if you plot the magnitude of that against frequency, and then the phase against frequency, you get a behavior looking like these two diagrams here. So as you increase the frequency of this through the of the input going through this particular little network, you're supplying something, and as you increase the frequency, nothing happens. There's a slow increase, and then right at omega 0, you get a peak. The gain at that point is 1/3, and then it dies off again to nothing. Look at what happens to the phase as well. The phase here, and you can work it out, but again, we'll do it more formally in signals and systems. If I give you a complex number, the argument of the complex number is the inverse tan of the imaginary part over the real part. So you can do that here. You have the real part, which is these two here, right, and the imaginary part here. So the argument of that, the inverse tan of that will give you what the phase angle looks like. And if you were to plot the phase angle for this, the second order system, is going to start at plus 90, as we have here. So it's going to start at plus 90, and then right at you reach F0, right there, the phase angle is 0 degrees, and then it goes back to minus 90. So you remember the Barkhausen criteria, whatever we have, if this is our network here, the open loop gain of this thing, we put this is part of the whole network. So you're taking the output and we're going to take part of this and send it back to the input somehow. The open loop gain of this, if the open loop gain somehow, we get the open loop gain to be, the phase, sorry, of the open loop gain to be a multiple of 2 pi, right? Starting at 0, so it could be 0 or it could be 2 pi, etc., etc. So 0 satisfies that. Notice that this particular one, as we pass the omega 0, that the phase at that single frequency is 0. The other part now is that the gain, we want the gain to be 1. Here, this particular network has a gain of 1/3. So what do we have to do? We have to pass this through some sort of amplifier that is going to give us a gain of 3. 3 by 1/3 will give us 1. So if we have those two things, so we find a way now of amplifying this. We already have the feedback part giving us the 0 phase shift, and we know the gain of this bit is 1/3. So we put it into our network where the gain is 3, and lo and behold, we have something to work with, which is what we have here. All right, so just summarize what we just said. So how do you get that to work now? So this is where now, notice this is the output of the circuit, and you remember how the feedback system works. This is the output here. This is the input, quote unquote, here. We are taking the output, passing it through the op-amp, and putting the input back in, right? So without any external factor at all, this particular oscillator now, or this particular circuit, is taking the output, passing it back through. This now has 0 phase shift. This part, the RC, has a gain of 1/3. We are just here to have a gain of 3, so that the overall loop gain is going to be 1. So how we design that, of course, you choose a reasonable value for C. So you start, of course, depending on the sort of frequency range, so you pick a value. Omega 0 is, going back here, and that was easy. Omega 0 is 1 over RC. So after picking C, you choose a value for R to give you, you know what omega is. You are designing the system, so you know what omega 0 is. So you choose the value of R. So you have the Wien-bridge part of the network functioning already. Then you pick a value for RA. Convenient. You pick 10K or something of the nature, not too small op-amp. So on the output you put a slightly larger resistor, not to load the device. So you pick a value for RA, and then you choose RB to make the gain of the op-amp 3. And of course, what you do is that you typically, instead of making it exactly equal to 3, you make it a little bit more. So instead of 3, instead of a gain of 3, you probably go for a gain of maybe like 3.01, 02, that kind of thing. I'm not talking about going like 3.5 or that, very slightly smaller. And then once you power up the circuit now, what you're going to get at the output here, you're going to get this thing giving you a sinusoid. So this is going to give you a sinusoid. The sinusoid is at omega 0. Because we have nothing else inside of here, the sinusoid is actually going to do this and eventually saturate. And then slowly it's going to do that. And then when it reaches as it approaches the power supply, it will start to do this. So it will behave like a sinusoid and then start to clip. And then if you don't do anything before, you're going to get something looking like this at the output. So in a later class, we're going to talk a little bit about stabilizing. There are very simple ways of doing that. But if we're very careful and resistor values don't vary too much and the values are chosen fairly carefully, it will take a little while before it actually saturates, and you get a few seconds worth of a very clean and pure sinusoid coming out of this circuit just by powering it up now. Yeah? Make sense? Everybody following? You have to read back what we did as well too, and listen again to the class. If anything I'm not saying is not clear, then of course let me know. So one thing with this though, before we close off here, one of the problems with this, right? Good. So at least two people are following. That's nice. Batting good today. If at any point in time now I want to change the frequency of this network, notice what happens here. I have two matching resistors here. No, that is not a matching resistor. I have two matching resistors, this and this, and I have two matching capacitors here and here. So if I want to change the frequency of this circuit, because everybody matches, if I change the resistor, I either have to change the resistors in pairs or the capacitors in pairs. So it is possible to get a multi-range or a wide range oscillator using the Wien-bridge circuit. But to do that now, you have to have an area where you switch both the capacitors and the resistors together. So a typical example of that kind of thing would be this circuit that we have here. The capacitors switch together. They use something called ganged switches. In other words, there's two switches. It's a rotary switch, one on top of the other. So as they turn the knob, the axle actually connects to two switches. So it moves. As they turn the knob, it switches A and A together. It will switch A and A together. Then it will switch B and B together, and so on. And once you have a particular range selected by those capacitors, then you can vary the resistance within that range by again varying the resistors themselves by having another pair of resistors, variable resistors, potentiometers that are also on the same axle, right? So the normal potentiometer that you meet already, what you have are two, one behind the other, and there's a common axle going through it. So as you turn the knob, the axle will turn both of them together. So it makes it a little more cumbersome, but you're able to switch from, for instance, the CA values might be low frequencies, audio frequencies, so like 10 hertz, maybe to 20 kilohertz. And as you go to the next range, you have 20 kilohertz to maybe 200 kilohertz. And then the other range, 200 kilohertz to maybe 2 megs. And then the other range from 2 meg to maybe 20 meg. You're not going to get much higher than that using these components, because using this sort of arrangement, because the higher the frequency you go, the smaller the capacitors you have to use. You then run into that limit that you would have learned in the op-amp, about the op-amp called the gain bandwidth product, right? So as the bandwidth increases, the gain drops, and there's an upper limit to this performance as well. And then, as I said, the capacitors get smaller, and it makes it harder and harder now to link very small units together without the capacitance of the wires that connect them starting to interfere. So you typically have an upper limit of this of maybe tens of megahertz, right? The lower limit is quite low. You can actually go to subhertz, as we said before. All right. So, any questions? Make some sort of sense? And keep in mind what we discussed about the transfer function behavior and the S equal to j omega, because we will cover it in, yeah, just now, Joshua. We will cover it in ECNG 2011 in some detail as to why it happened. So the signals explanation will be of course here. The electronic explanation is in this course. All right. So Joshua, the link switches will be close together in space. Right. The link switches are actually one on top of the other. Right. So it's two rotary switches. Right. They're actually one behind the other, and there's a common axle connecting both. So as you turn one, the other, both of them turn together. Right. So they physically, yes, basically tied together. Same thing. So you use a pair for the capacitors and you use a pair for the variable resistor as well. Yeah. So you all right? Yeah. All right. So at this point, so let me stop the recording here.